Let's look at a couple of application problems. Starting with exercise number 62. A honeybee population starts with 100 bees and increases at a rate of n prime of t bees per week. What does the expression 100 plus the integral from 0 to 15 of n prime of t dt represent? So there are various ways we can go at this. I'm going to talk about two of them. One of them is just sort of the kind of direct, uh, uh, you know, not a fancy approach. We just can say, all right, well, let's try this net change theorem that we have, right? We have 100 plus the integral from 0 to 15 of n prime of t dt. And the net change theorem presented in this section says that the integral of a rate of change, this is an n prime, this is a rate of change, is the difference of the values. So that would be n of 15 minus n of 0. That expression is really just in terms of the framing, our interpretation of it. This is no different from what the fundamental theorem of calculus part 2 tells us from the previous section. Since we have a derivative here, FTC2 simply tells us that we can evaluate this integral by taking n of 15 minus n of 0. So again, the net change theorem is more in terms of interpretation and phrasing than it's our perspective on the thing rather than a new computational technique. And to continue this thing, let's see what we know. What would n be here? Well, we're told that the population increases at a rate of n prime of t bees per week. So t is probably time. N prime is the rate of change measured in bees per week. So n itself should be the number of bees in the population, right? So n of 15 is the number of bees in the population after 15 weeks. N of 0 is the number of bees in the population after 0 weeks. In other words, the initial population. We're told the population starts with 100 bees, so that means that n of 0 should equal 100. So now we see we have 100 plus n of 15 minus 100, and that leaves us with just n of 15, which is the number. There's a suggestive labeling here with n for number. The number of bees in the population after 15 weeks. So this is what this expression here represents. So that's one way to look at this. Another approach, we could go at this a bit more intuitively and say, all right, well, let's start off with figuring out what the integral represents. Let me rewrite this down here. The integral from 0 to 15 of n prime of t dt. Okay? And maybe let's think about the units here to help guide us, do a little bit of dimensional analysis. We're told that n prime of t is measured in bees per week. So this is bees per week. dt is a very, very small change in time. So what units would time be measured in? Well, looking at the way this is phrased, time is probably measured in weeks, hopefully. So if we measure time in weeks, and we think about this product, there's n prime of t is measured in bees per week. dt, the change in time measured in weeks, weeks cancel, and we're left with units of bees. And we have a sum of numbers of bees. N prime of t was the rate of change in the population in bees per week. So this would be adding up the actual change, not the rate of change, but the actual change in bees from 0 to 15 weeks. So that tells us that this integral is the amount of increase of bees in the population from the starting point to 15 weeks. This 100 represents how many bees we start with. So we're starting at 100 bees. We're adding the amount of change from 0 to 15 weeks. What we end up with then should be the final value after 15 weeks. So the number of bees in the population after 15 weeks. That's a way to get that by kind of reasoning through the concepts of what this means. Here's a way to do it just numerically and symbolically using, invoking the net change theorem. Whichever way you want to think about that. Those are a couple different ways to view this problem and interpret what's going on. Let's take a look at another example. Here we're told that the traffic flow rate past a certain point on a highway is Q of t, which equals 3,000 plus 2,000t minus 300t squared cars per hour, where t equals 0 is 8 a.m. How many cars pass by in the time interval from 8 to 10 a.m.? So, let's try setting up an expression to describe this, and then kind of evaluate that. This Q of t is a flow rate. It measures cars per hour, right? So if we take Q of t, actually, let me move that down a bit. Let's write this down here. Q of t is measured in cars per hour, right? We want to know how many cars pass by over a particular time interval. So we would have to multiply by some number of hours, right? But this is continuously changing. If Q of t were constant, if this were a constant rate, you could simply multiply by the number of hours that pass, the hours would cancel, you'd get the number of cars. But it's constantly varying. I shouldn't say constantly varying, it's continuously varying. So whatever Q of t is at any particular instant, the time that we multiply by would have to be a very, very tiny time interval, infinitesimal. Let's multiply by a differential dt. This has the right dimensions now. This has the dimensions of cars. This is how many cars pass at the instant t. But that's also infinitesimal, right? So we need to sum all of these to get a total number of cars. We want to sum it over what? Well, we want to sum from 8 to 10 a.m. We're told that t equals 0 corresponds to 8 a.m. This business about t is cars per hour. The implication here is that t should be measured in hours. So we're going from 8 to 10. Starting at 8, that's t equals 0. 10 a.m. is 2 hours later, so that should be t equals 2. So we have the integral from 0 to 2, q of t dt, is an expression that should tell us the total number of cars that have passed this particular point on the highway over this 2-hour period. So that is the integral from 0 to 2 of, we need parentheses because we have more than one term, and we need to have all of that with our dt. So we have 3,000 plus 2,000t minus 300t squared dt. Now we have a definite integral to evaluate. Let's find an antiderivative. We get 3,000t plus, we have a 2,000t. When we integrate that, that becomes a t squared over 2. So canceling that is 1,000t squared. Minus, we have 300 times this t squared. Integrating t squared is t cubed over 3. So that simplifies down to 100t cubed. There is an antiderivative, and we're going from 0 to 2. Again, because this is a definite integral, we don't need to add a constant here, because we'll be subtracting whatever that constant is will cancel itself out. So we can just take the constant to be 0 and not worry about that. Alternatively, remember what the fundamental theorem of calculus part 2 says is that the function that we evaluate at these two ends can be any antiderivative. So we can choose that constant to be whatever we want. We'll just let that constant be 0. So now we just need to evaluate this thing. We have 3,000 times 2, which is 6,000, plus 1,000 times 2 squared. 2 squared is 4, times 1,000 is 4,000, minus 2 cubed is 8, so we have 800. So we have all of that. Minus this thing evaluated at 0. Well, we have 0 plus 0 minus 0, that's 0. 6,000 plus 4,000 is 10,000, minus 800 looks like 9,200. And what should this be? Well, this should be cars, right? The hour is canceled. This should give us cars. 9,200 cars. Let's see if that makes sense. We're asked how many cars pass by in the time interval from 8 to 10 a.m. That sounds good. 9,200 cars pass by in that particular time interval. So there we go. Thinking about the dimensions, I was doing a little bit of dimensional analysis there. You don't have to, right? And think about this, just from the net change theorem perspective. The flow rate tells us the rate of change of how many cars have passed a certain point. So to get the number of cars that pass from 8 to 10 a.m., you just, set up that integral where you're using the rate of change. Q of t is a rate of change. It is a derivative of the number of cars that have passed. So you can think of that from the perspective of the net change theorem a little bit more formally and construct your integral that way. There are lots of problems like this where we have some sort of a rate of change and we want to interpret that and figure out what the actual difference between certain values was. And that's where our integral comes into play. We can add up all of those kind of infinitesimal values, these momentary amounts of change that we get, and see what we end up with there.